Awesome. All right, so I'm assuming all of us in some way have a little familiarity with Alexa, since this is kind of a slightly deeper Alexa conversation talk we're going to have today. So my name is Jeff Blankenburg. I work on the Alexa team, and I spend most of my time out talking like this, talking to developers about how to use the latest cool stuff, how to build things for Alexa, how to think about conversations, how to design. And so I'm here to talk to you guys only for about the first 10, 15 minutes about what entity resolution is, how it works, and I'm going to bring up people much smarter than me to talk about the real science behind it and how we really think about entity resolution, not only in Alexa skills, but across the entire platform. So with that, I'll get right into it. The first question I have to answer for everyone is, what is an entity? Some people don't really understand what this term means. I mean, you probably learned it when you were in school, but when we talk about programming and talk about Alexa, an entity generally is the idea that it's a thing, right? In some cases, we might think of this like an object, but it's usually something more specific or bigger than that. So we think about something that we want to model or something that we want to be able to refer to. And let me give you a quick example. I think this is an easier way to go. So let's say a user wants to know something about Jordan, and they indicate that to us through whatever system they're using. Maybe it's a search engine, or it's Alexa, or whatever. And so they say, hey, tell me about Jordan. Do they mean the country of Jordan? Maybe that's what I have marked on the map here. Maybe that's what they meant. But I would think most of you, especially if you saw some of our special guests that have been here this week, we have an affinity for basketball players. Maybe we were thinking more about this guy, right? Tell me about Jordan. They could certainly have meant that. But he had a massive influence on things other than just basketball. Maybe when I want to know about Jordan, I actually meant his shoes, right? And so how do I know when I think about entities, how do I know what the user meant? How do I distinguish that? And for those of you that have worked with Alexa before, you know that if I was building a search engine, if someone asks me about Jordan, I would just provide them a list of results, and they would let them pick. Which one did you mean? Which one do you want to really know about? But with voice, we don't really have that luxury. We have to pick the best possible option out of all the options that might be available, and we have to pass that along to the user as the thing. Here's the answer to the question you gave me, and I have to hope that I kind of have the best answer. So that's what we're talking about today, is entity resolution. How do we resolve down to the entity that we really want the user to be able to have and make them feel like they got the right choice? And how does that all really work, right? So this is not a representation necessarily of entity resolution, but the idea here is, how do we figure out, based on all the options that are available to us, how do we narrow that down to identify the thing based on context and all the other information that we have available to us? How do we know what the thing is that we should be presenting to the user? So before we dive deep into entity resolution, I don't know what everyone's level here is for Alexa development. I'm hoping there's some experts like Andrea in the room that know what's going on, but I think there's a lot of people that maybe are familiar with Alexa. So I want to give you a quick background on how Alexa works. I'll give you a cool demo of a skill that I've built, and then we'll walk through the individual steps that were required for that entity resolution to happen. So the first thing to understand about Alexa is this is kind of the diagram of the process when we think about Alexa and a user talking to the device. So on the very far left side, you can see the user, and they are saying something, and their words get carried into the Alexa device that's in their home or their office. And the first thing that happens is there's a wake word that gets spoken, right? So the user says Alexa, or they might say something like computer or echo. You can set the wake word to a couple of different phrases on your device. Once that happens, we start recording the words that have been said after that wake word. There's a term on here called beamforming. This is also another very cool thing that's related to the hardware. There are multiple microphones mounted on a device. And so when a user speaks, the microphone there's an array of microphones, usually arranged in a ring. And the microphone that is closest to the sound, that one will pay attention. And all of the other ones will use the data they hear to cancel other noise out, so that it's really focusing directly on the direction I'm speaking. And you'll notice, I'm not going to demo it here because with microphones and stuff it gets weird, but this is an Echo Dot, and there's a ring around it. You'll actually notice on your device at home, when you speak to it, it will point in the direction you're looking. So it'll light this edge up or this edge, depending on where you are standing. So that's what beamforming is. So we take the wake word, we take the words that have been recorded, and we pass that out to the cloud, which is my nice big cloud here in the middle. And we do a few interesting things with this, right? We have to do speech recognition. We have to figure out what it is you said. And so the first thing we do is take the waveform, the audio that was recorded, and turn that into text so we can do something useful with it, right? So that's speech to text. The next thing we need to do, though, is what we call natural language understanding, or NLU. And what NLU does, the best way for me to equate this is there's lots of ways you can say things. And if you've ever been in a relationship, you know that what you say is not always what you mean. And Alexa needs to be able to understand that as well. So what natural language understanding does is try to say, okay, they said these words in this order, what do they mean? And if I were to walk up to any of you and say, hey, what's it like? There's no contextual words in that sentence at all, right? What's it like? But all of you know, based on context, that I'm asking you what it's like outside, right? What's the weather? What's going on? Is it raining? And you're going to give me an answer that probably reflects that. Those kinds of things are things that natural language understanding provides. It provides that analysis and contextual understanding based on the millions and millions of other conversations that have ever been had with Alexa before. We see patterns, we can identify slang. There's all sorts of things that start to bubble up and allow us to understand what a user's saying, even though we may have never seen that word used in that way before. Okay, so we have the recording, we've turned it into something we can use. Now your code, what goes on inside your skill, needs to be able to access that information. So we take that, we create a nice big JSON file, and we pass it off to your service. This is where your code lives when you build an Alexa skill. And this is where you can do whatever you need to do with that information. So you know as much as you can about the user, right? You have their anonymized user ID, you have what they wanted to do, what they wanted to accomplish. We call those intents. And in those intents, they encode what the thing is they're trying to accomplish, right? If my skill was a DVD player, my intents would be play and pause and stop and fast forward and rewind and eject and the things you can do on a DVD player, right? I wouldn't have on a DVD player an intent for order a pizza because my DVD players don't order pizzas. I don't know if you guys have one. I've seen some really cool technology here. But I'm guessing your DVD players also don't order pizzas. So you wouldn't have an intent for a DVD player to order a pizza. But you would have things that DVD players generally do and the things your users would expect your skill to do. So once we've done that, the users indicated their intent, we've understood what they want to do, we craft a response, a set of words, and we pass that all back through text-to-speech, right? We take the text that we've generated and we turn that back into Alexa's voice, and what's really nice is that everything that happens in the cloud I don't have to do anything with. I don't have to create audio files, I don't have to generate the speech, all I have to do is say, Alexa, say this next, and she just does it. So that's more or less how it works. We can do some really cool things with that speech. We have something called SSML, Speech Synthesis Markup Language, which allows you to add sound effects or all sorts of emphasis to words. There's all sorts of cool things you can do to make sure that Alexa says things the way you want her to say them. And then finally, we can do things like streaming audio. And we pass all of those responses back to the user in one of two ways, back through the audio device they talk to, but we also have something called cards, which write core information into the user's Alexa app so they can save it for later. So if it was directions or maybe a stock price, they don't have to look it up every time now. They can just open the app and be like, oh yeah, it was $100 earlier today or whatever it is. So that's the process for how Alexa works. Those are the things that happen when a user interacts with a skill. So I needed to build a skill, and I wanted to do something interesting. I figured there's nothing else out there like it. Let's do something where I can look up information about movies and find out who's in it. I can't imagine this website doesn't exist already, but I'm going to build it as a skill because that seems like a thing to do. So I called it MovieCast Database. I'm going to give you a very quick demo of how this works so you can see the challenges that I run into with entity resolution. Alexa, open MovieCast Database.
Welcome to the MovieCast database. Which movie do you want to know about?
Marvel.
I heard you say Marvel. I have two potential matches for you. Did you want Marvel's The Avengers or Captain Marvel?
Captain Marvel.
Captain Marvel stars Brie Larson as Carol Danvers, Samuel L. Jackson as Nick Fury, and Clark Gregg as Agent Phil Coulson. What other movie can I help with?
Avengers.
You asked me about Avengers Endgame, which includes Robert Downey Jr., Chris Evans, Scarlett Johansson, Chris Hemsworth, Josh Brolin, and many others. What other movie can I help with?
Stop.
Okay, goodbye.
So what I want you to see there is I took two different approaches. The first time I said Marvel, and it said, I don't really know what you mean. Did you mean Marvel's the Avengers, or did you mean Captain Marvel? Those both have the same word in them. And the second time, I said, I want to see the Avengers. And in that case, I just made my best guess based on the information that was passed back to me as to which movie you probably meant. There's actually 5 answers, and I'll show you the code that was generated by that interaction we just had. But there's 5 different movies in the Marvel Cinematic Universe that actually have the word Avengers in the title, or at least the word Avenger. One of them is Captain America, the first Avenger, and then there's the 4 Avengers movies that have come out. So how do I know which one to use? How do I understand this stuff? That's what we're going to dive into now. So the first thing to understand is that I had an intent in my skill called movie intent. And what I do when I define an intent is give it a bunch of sample phrases that users might say. So in my case, I just said Marvel, but I could have said which actors were in Marvel, or what were the actors in Marvel, or whatever. These are all sample phrases. This is not a static list. This is not like an enum you might see in code where if it's not in this list, it doesn't exist. Alexa uses this as training data to understand the kinds of things your users will say. So even if it's not specifically in this list, if it resembles these kinds of statements, it will still work just fine. But I generally recommend for any intent, you should have 7 to 12 samples at a minimum. If you find yourself going over 100, you might want to rethink how you're designing your skill, because 100 seems like a lot. That's probably overkill for what you're trying to accomplish. So that's a movie intent. In my movie intent, I had that movie slot type. You can see that here. It was highlighted in each one of my phrases. Here I have my actual slot called movie, and this is where I have a list of all of the movies that are available in my skill. And this scrolls much further. I'm just showing you a screenshot of the top of it. And you can see that I have Avengers Endgame, I have Captain Marvel, I have Ant-Man and the Wasp. And then on the right-hand side, you can see that I have Endgame listed next to Avengers Endgame, and I have Marvel listed next to Captain Marvel. I want to make sure that if they only say those words, if they just say Endgame, I want to make sure that I'm still capturing that as well. Because movies have nicknames, right? And we want to make sure that even if the user says the nickname, that we're still catching those kinds of things. So I do that. I recognize that Avengers is in both of those. And so those are the 2 results that get passed back to me. So let's talk about what it looks like to get this information passed to me. We're going to jump into some JSON here. This is the JSON that gets sent to my skill. This is what I parse and use to respond to my user. And so I'm going to point out each of the interesting pieces of this as we go through it. So the first thing to notice is that I notice they hit the movie intent. Alexa tells me, hey, they indicated they're using the movie intent, so you want to do something related to that. The next thing to notice is the slot value. This is the thing the user said. I said Avengers to the skill, and so it passes to me and says, hey, the slot movie, the one you defined, the value that they're passing through is Avengers. So you're going to want to use that to make some decisions about how you respond to your user. The next thing is where we get into the entity resolution piece. This is where it helps me make some decisions. You can see down here that I have this resolution. Resolutions per authority. And so my authority, if you look way out on the far right-hand side, it says .movie. That's the name of my slot. So it's using this as a reference guide for the things that the user might have indicated. And then what it provides below is a list of all of the different things in my slot that potentially matched the utterance that the user made. It's giving me this up front. I don't have to make another round trip. I don't have to make another call. I have this information right away, and I can see that I have 5 different options. So the way that these results are provided to me, based on Alexa's understanding of what's going on, it's ranking them from top to bottom as the one that seems the most likely. It doesn't give you a score, so that doesn't mean that number 1 is absolutely the best and the other 4 maybe. It could be that they're all equally ranked as well, and it's just doing its best to rank them in an order that makes sense. With my skill, there's no additional information, there's no additional context to give me an indication when you say Avengers, which movie you meant. So the context here is likely that Endgame is the most recent Avengers movie, and that is why we're presenting that one as the first option. But as I did with the Marvel reference, I said, do you mean Marvel's the Avengers or Captain Marvel? In that case, it would provide me both of those, but I could, instead of presenting a list or saying, is it this one or this one, I can just make that choice, right? So as you go through each of these steps, it's important to understand what you want to do for your users. Do you want to just make the best guess? Or do you want to use all these options and list 5 things off, right? If someone was building a pizza skill, do you want to say, okay, you want to order a pizza. Here are the toppings you can have. pepperoni, sausage. Like you could just go on and on and on. You'd rather just say, what topping do you want? And when they say sausage, you can say, okay, we have Italian sausage, or we have a spicy andouille sausage, or whatever it might be. And you can narrow those things down for the user, or you can just say, oh, we only have the one kind of sausage, let's just go. Anything that makes it easier for your user is the right direction to go. So this is the core of entity resolution inside an Alexa skill. This is what we use to get from A to B. This is what we use to help make decisions about what the user meant when they're talking to our skill. So the next thing that I want to do is start to bring up some of my team. I have a gentleman named Avnish that's going to come up and talk about the science behind this. And so with that, I'm going to turn it over to him. Thank you guys for having me.
Thank you, Jeff. Thanks. Thank you, Jeff, for introducing me. Hello, everyone. Thank you all for being here today for this presentation. My name is Avnish Sikka. I'm a senior manager on Alexa AI team in Amazon. So let's get started. So why is entity resolution such a difficult problem? Why is it so hard? Why is it so challenging? I will show this through a set of use cases for various kinds of conversations our customers have with Alexa today. These use cases will exemplify the need for entity resolution in Alexa. So let's say we have a user talking to Alexa devices. I'll show you some use cases. Alexa, turn on the desk light. Alexa, call Stuart. Alexa, play YouTube. Alexa, what's the weather in Las Vegas? Alexa, what's 3 Mars about? Alexa, play Frozen. Alexa, find me the nearest Starbucks. Alexa, volume up. Alexa, 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 Alexa. People want her to do so many things, and she's always there serving those requests. How does she do that? In general, these use cases fall under 3 kinds of interactions. First one is task completion. Under task completions, you can have entities or no entities. Examples of entity-based task completion are Alexa, watch Infinity War, or Alexa, turn on the kitchen lights. Examples of non-entity based tasks are Alexa, volume up, or Alexa, set an alarm for 5 minutes. The second kind of interaction is question answering. You can have questions with entities in it. Example, Alexa, what's 3 Mars about? Or Alexa, who is Robert Downey Jr.? You can also have questions that don't have any entities. Example, Alexa, what's the time? Or Alexa, what's the tallest mountain in the world? The third kind of interaction is conversational. Sometimes users want to have a conversation with Alexa even when they do not have a task or a question in mind. People just want to talk to Alexa. To encourage users engage with Alexa in a more natural way, Alexa supports conversational bots through Alexa Prize. Alexa Prize is a global university competition committed to advancing the field of conversational AI. Hopefully, some of you got a chance to watch the presentation about this on Wednesday. Now, Rohit also, in a keynote presentation, talked about Alexa conversations. This is to enable developers build conversations that matter to Alexa customers with less effort, less code, and less data. In this session, I'll be talking about the entity-based task completion. There are 2 challenges to find the entity in a request. First one, how does Alexa understand entities in user natural language? Let me show you with a simple example. Alexa, play the movie Avengers Endgame from Amazon Video. In this case, Alexa understands entities in user request using the NLU techniques that I'll get into later. Now let's take a more difficult example. Alexa, play the opening song in Robert Downey Jr.'s latest movie. As you can see, the entity name is not even there in this request. How does Alexa find these kind of, support these kind of use cases? We'll cover that in some of our challenges that we're working on. For now, let's focus on the simple use case. Once we have the right entity, that is a movie title in this case, the second challenge is, how does Alexa launch the service provider with the right set of actions and route this request to that service provider? Service providers could be Amazon Music, Spotify, Apple Music, Pandora, iHeartRadio, and so on and so forth. Now let me explain how does NLU system or natural language understanding system interprets user request. So let's go through the same example that I had in the previous slide. Alexa, play the Avengers Endgame from Amazon Video. So let's talk through how these understandings are produced by the NLU system. So NLU generates domain, intent, and slot classifications. So in this request, the domain is a movie. The intent is play movie intent. And the slots are media type, which is movie, movie title, Avengers Endgame, and the service provider, which is Amazon Video. So now let's talk about how these understandings are generated. NLU uses deep learning models to perform the domain intent classification and uses named entity recognition to generate these three slot types. These models are trained using active and transfer learning with domain and language specific features, which is what helps Alexa scale. Now, Jeff had previously talked about how the user request flows through end-to-end system. In this slide, I will talk about where does entity resolution sit in the Alexa architecture. So after the user has set a request to the device, Alexa voice service receives this request, receives the audio, and sends it to the automatic speech recognition for further processing. Automatic speech recognition, or ASR, sends this request back to Alexa voice service. From there, it goes to natural language understanding. Natural language understanding service converts this text into entity action pairs, and the request is then sent to the service providers to support actions. Providers then help serve the content for these entities, and the final response is sent back to the user through text-to-speech service. In this session, we are focusing on the block on the right side, which is a natural language understanding and entity resolution. So on a broad level, there are primarily 6 categories of difficulties that are there for entity resolution. I'll explain these one by one. So let's start with the first one. Oops. Spoken query. So as you know, users talk to Alexa in voice, but the search is in text. Spoken to written form could be different. For example, when I'm talking to Alexa and I say a number, that could be very different in a written form. For example, if I say, Alexa, play U2, Alexa might hear it as alphabet U and number 2, or she might hear it as play U2 with the 2 spelling or TWO. How does Alexa know which is the right entity to search in this case? The next challenge is homophones. If a user says, Alexa, call Stuart, it could mean Stuart with this spelling that you see on the slide, or it could be S-T-E-W-A-R-T. How does Alexa know what's the right Stuart to call? The third case is non-dictionary words. We always have it, right? Some people, use a name like Alexa, play Pink. In this case, Pink is not spelled as P-I-N-K. It has a different spelling. So how does Alexa know what's the right entity to find in this case? Then we also have synonyms. If I have a device on my home that I've called it as a desk lamp, but I want to turn on that light by saying, Alexa, turn on the desk light, Alexa should still be able to recognize that request and take actions on that entity. Lastly, like Jeff also mentioned in his session, talking to Alexa like smart assistant is very different from a web search. In a web, you can type a query, you'll get a bunch of results, and you can select the right one. So how do we solve these problems? So we solve these problems through query expansion and fuzzy matching. Once we generate the domain, intent, and slots from NLU, we use NLU slot values to construct the search query. There are several techniques we apply to expand the query, such as alternate query terms. We use ML-based models to build search query terms using synonyms, homophones, aliases, and alternate names. For example, we just saw in the case of U2 versus U2, there are different spelling variants. Then we also use transliteration. Transliteration is basically converting from one script to another script. So in Japanese, it's pretty common to have 3 or 4 scripts in the same request. So in this example on the screen, if a user says, Alexa, play Justin Bieber's What Do You Mean? We need to process a blend of kanji, katakana, hiragana, and romanji. We have to translate all these inputs in different scripts to one script to optimize the search recall and match against the tokenized search index. We also use fuzzy matching. Basically, we use lexical and phonetic-based searches using ML models to re-rank the results. Example, the case that I described is called Stuart. We will use ASR phonemes to match against all the pronunciation of the word Stuart and stored in the search index. This is also useful to support multiple languages and non-dictionary words. Next level of difficulty is contextual awareness. Context is very important in a conversation. So for example, when I walked onto the stage, I thanked Jeff, and that was Jeff Blankenburg, who likes to call himself as Jeff B, by the way. So people know, right? And people had the context that when I thank Jeff, it's the Jeff who was part of this session and not the other Jeff B that you guys might be thinking about. But let's come back to the entity-based task completion. Context is also important in a task that involves entities. So I'll show this with, again, some examples. If I say, Alexa, Frozen, or Alexa, play Avengers, how does Alexa know whether the Frozen or Avengers is a movie, is a book, or is a song? To handle such difficulties, we use context-aware search and re-rank the results based on the context. So what I meant by context is, it could be a device type in this case. If I'm saying this request on a device that has a screen, probably it's movie. The next challenge here is based on the context. For example, if I say, Alexa, find me the nearest Starbucks, or Alexa, play Kiss FM. Based on my location, the entity return could be different. It has to be a relevant entity. So the next kind of context we have to handle is the location, user's location. Third thing is personalization. Based on my interaction history, I might be a user that might like to hear more audiobooks or music. So based on that context, you return that entity. I will now discuss the context-based re-ranking in detail. So let's take the simple example, Alexa, play the Avengers. NLU can generate multiple interpretations for this request. It could be a movie. It could be the song, theme song from Avengers movie, or it could be the audible book. It's hard for NLU to make a final ranking decision because all these entities are valid and popular. So in this case, user might actually want to hear the movie song rather than watch the movie. So we use entity resolution results with contextual signals like that I covered in the previous slide, device type, user preferences, history, things like that to re-rank the results and return the right entity to the user. Now, previous slides showed the difficulty of identifying the right entity within a single language. The next level of difficulty is when you have a mixed language. You might be referring to an entity which is in a different language than the request itself. As Alexa has expanded into supporting more countries and more languages, this becomes a challenge. So again, let me use a simple example to explain this further. If I say, Alexa, play Despacito. Despacito is a Spanish song name, but rest of the request is in English. Let's take another example, complicated. If I say, Alexa, play Jab We Met movie, in this case, the entity name is Jab We Met, and that name is actually in 2 different languages. So it's hard. So how does Alexa do this? We address these kind of problems by using a language agnostic search. Taking the second example to explain this further, we use Hindi and English tokenizer and generate 2 locale specific tokens to ingest these in one single search index. Now, during the runtime, when ASR and NLU output is Jab We Met, because both the tokens of the word Jab are in the search index, we actually are able to find the right entity and return that to the user. Without this solution, we had to set up individual indices for each locale separately. Now, instead of using many locale specific indices, we just create one language agnostic index. This enables Alexa to retrieve the entities more efficiently. Next difficulty is it's hard for us to know whether the returned entity is correct or not. We need to infer user actions or signals. So that means we need intuitive feedback to know whether the returned entity user was satisfied or not. Let's see how we address this. I'm going to start with an example again. If a user says, Alexa, play hello, and Alexa returns an entity, but that's not what the user wanted. Now, the user reformulates the query and tries to be more specific. What they say is, Alexa, play hello by Adele. Now, this is what user wanted, and when Alexa returns an entity, user plays that song, hears that song for a longer duration. So that's how Alexa learns that this is what user wanted. So next time when the user says, Alexa, play hello, Alexa has already learned. So how do you solve these kind of problems? We have developed user feedback-based learning pipelines to address this issue. There are 2 components of this pipeline. First one is automated query reformulation. So in this case, we identify user friction based on the play duration or termination. User might have said, Alexa, stop, or barge in. The second one is user preference-based re-ranking. So user might have a preferred content. There might be some users that want to listen to the song or audiobook or watch video. We learn that preference and return that entity. The second one is collaborative filtering. If we have a group of users that are interested in listening to a particular set of music, we kind of profile those users and return the similar entities to another user who might fit in the same profile. The third is preferred provider. So in this example, if user also said, Alexa, play hello by Adele on Amazon Music, they don't need to specify that service provider again and again. Alexa has already learned it. The next level of difficulty is search space. Developers want to reduce the search space to be fast and to be more accurate. Let's talk about how we address this. So let's say there's an Italian food skill. I know it's getting close to lunchtime, so hopefully I'm not going to make you hungry with this example. But so let's say there's an Italian food skill and user wants to order chicken marsala. Now, due to some background noise or user accent, chicken marsala becomes chicken masala. Valid mistake, right? So how does Alexa find out what user meant in this case? Since this skill handles only Italian food, entity return in this case is chicken marsala because there is no chicken masala present in the Italian food menu. To address such category of problems, what we have built is dynamic entities. I will explain a few benefits of dynamic entities. The first one is entity-based models. Because there is a limited set of entities that are valid for this dialog or for this skill, the ASR, the NLU, and the entity resolution models are based towards a smaller set of data. The second one is personalized experience. I might have a skill where related to maybe a food or a beverage or things like that, where I have personal preferences. Based on my preferences, the search will be limited to what I prefer. The third one is runtime request. Because entities are loaded during runtime are valid only for that short duration of time. In the next transaction, you can actually have new set of entities. Ask provides an API to specify a list of valid entities in a multi-turn dialog. The fourth one is localization. Some entities might be valid only for a particular region. For example, it could be music, it could be food, drink, things like that. Using localization, we again limit the search space. And the last, and this is a big benefit that a lot of Alexa developers have kind of told us, that for catalogs that need to get updated frequently with the data, there's no need for recertification. So that's a big benefit. So many skills have already benefited from this dynamic entity feature. There are like few skills that are in top 100 skills used. They have reduced their errors by up to 98% using this feature. So I'll further explain dynamic entities using an end-to-end example. So let's say there's a flight booking skill and user is in Boston, wants to go to Seattle. So user says, Alexa, ask flight booker to book me a flight home. Alexa knows this user is in Boston. Alexa also knows home in this case resolves to Seattle because through personalization. Alexa also knows this user prefers JetBlue and gives user this few options. Confirms the source and destination, like you want a flight from Boston to Seattle, gives some options on JetBlue, gives 3 options, flight number 67, 184, and 416, and asks users which one do they prefer. And the user responds with flight 400. Because the search space is limited, Alexa is able to figure out that 400 here actually means 416 and doesn't ask for any clarification. She goes ahead and makes a reservation knowing that this user actually prefers an aisle seat. So, uses that information to make the flight reservation. Because of all of this, the experience for both developer and their customer is now much better because of limiting the search space. Now, when you have so many skills with so many catalogs, with so many entities in so many different languages, obviously the next difficulty is scaling, which is not a bad problem to have actually. This just means we are doing good. So during past 4 to 5 years, as you can see in this graph, the number of Alexa skills have increased a lot. Number of catalogs and number of entities in the catalogs have also increased. So as number of service providers. Number of device types have increased, device types with multiple modalities and multiple capabilities. Number of locales have increased. It is becoming a tougher job to find the right entity and the right service provider for a given slot and return that to the end user. We still need to get the right entity and get it fast. So latency is also something we cannot ignore. Like Jeff explained previously in this session, Amazon has worked to help developers provide a solution to the ER problem. We have enabled developers to write their skills using the ER features supported by Ask ER Toolkit. Skilled developers don't need to worry about ER problem, and they can focus on the business logic. ER models are generalized and optimized for searching entities across many service providers and catalogs and domains. Now that I have explained all the difficulties, challenges, and the ways we address them, let me mention some future challenges as well. Entity recognition is critical for all kinds of Alexa conversations. As we just saw, when entity name is present in an Alexa customer request, it's a hard problem. We have all experienced situations where we don't remember name of an entity, name of a movie, name of a song when we're talking to our friends. But we still want them to be able to understand what we're trying to say. This is called implicit reference of an entity. This is an even harder problem as we make Alexa more conversational and intelligent like a smart assistant should be. I will invite my colleague Yue on stage, who's going to explain challenges like this and many more. Thank you.
Thank you. All right. Hello, everyone. I'm Yue Liu, working with Alexa AI Natural Understanding team. Thanks, Avnish and Jeff, for the introductions. As Avnish just walked us through a list of existing technologies for ER to address some of the challenges we are facing today when entity names are directly referenced. Now let's try to fast forward a little bit into the future. I would like to show you what we are working on now to address some future challenges when there are implicit references in the user utterance. But first, let me walk through some example to help you understand what do I mean by implicit reference. Say, yesterday, you or your friends really want to watch some movie. How about some movie from Robert Downey Jr., right? You may want to watch the latest one, but you don't happen to know the name of the movie. You may ask Alexa, say, Alexa, play Robert Downey Jr.'s latest movie. Alexa will know, based on the knowledge from IMDb, for example, the latest movie from Robert Downey Jr. is Avengers Endgame. Then Alexa will be able to transform this utterance into something like, Alexa, play Avengers Endgame. In this case, we will translate this difficult problem into the existing problems, right? We do a direct reference, just do the entity search on the name. But now, another day, you and your friends are saying, we really enjoyed the song, the opening song in that movie. In the beginning of that movie, there was some played, but we don't know the name of the song. What are you going to do now, right? You may ask Alexa again. This time, the utterance will be more natural and interesting, I think. You may say, Alexa, play the opening song from Robert Downey Jr.'s latest movie. As you can see in this example, it's really hard for us, for ER, to understand the entities because the name is not here, right? And for the ER system now, we not only need to know, okay, Robert Downey Jr. is the entity name for the artist, but also we need to know the list of movies he played, which one is the latest. In the end, right, we also need to join with the database from music domain, right? It's a totally different database now. With the knowledge from the music played in that movie, which one is the beginning played, right, the opening song. In the end, we will figure out the name of the song should be Dear Mr. Fantasy by Traffic. So now, as you can see in this example, if we only apply the existing ER solutions, we cannot solve it because it requires knowledge to understand the implicit reference in this utterance, as well as the relationship between the implicit entity name as well as the actual target entity you are searching for. To address this, we are building the entity action based knowledge graph. So what's this entity action knowledge graph looks like? Let's again, right, try to using some examples to help you understand. Actually, we build the knowledge graph by constructing the semantic representation of the utterance, as well as the provider capabilities. In this example, play the opening song from Avengers Endgame. In this utterance, play is the action. The opening song from Avengers Endgame is the entity. With the semantic representation, we build the graph, which has the entity action links, which describes their relations. This knowledge graph takes the search query from a component called entity-centric query understanding, and then it will return a list of entity action pairs along with the action to provider links, which pointing to all the providers who can support such action, have the capability. Now, with this action link to the provider, we will be able to route the traffic to the right provider accurately. But you may ask, what the entity action provider links looks like? Let's use some direct reference example to visualize such relation. For example, you say play the movie Avengers Endgame. Now, in this case, the Avengers Endgame, that movie entity, will be used to construct the graph. We're also recording all the properties for such movie entity into the graph. And then we connect this entity to all the possible actions you can think of. For example, for movie, we will connect to book a ticket, or you can say play the movie, play the trailer, or just asking some review ratings. Now you can see with the entity action pairs, we will be able to figure out some level of relationship, right? But after we know that, we also need to find out who other providers can support such action lists. Then we need the relation between an action and providers. For example, if you ask Adam Tickets to book the movie tickets, you may also ask some other providers such as Fandango. For play the movie or trailer, we may ask Prime Video. For asking the review, you may see something from IMDb or something from Adam Tickets, right? There are so many different combinations, as you can see here. If we make this even more difficult, think about restaurants use cases. You can ask for the menu, book the table, asking opening hour, right? There are so many different levels of actions can be provided. As you can imagine, there are many types of entities and actions here, and also many of the providers. How are we going to representing them semantically, right, in the same knowledge graph? First, we define Alexa ontology. This ontology, it is organized as a graph as well. It defines the entity types as well as action types. Types are also contains a list of properties such as entity facts or action parameters. Types can also have children types. They are in hierarchy. The children types will inherit all the properties from the parent. Entity type can also link to another entity type or action type by its properties. For this given example, movie is a child type under creative works. As you can see, there are multiple properties in this movie entity type. Movie actor, composer, country, and the movie actor, for example, can be connected to another entity type called people. This people type actually have a more detailed information about the person in that movie, such as a birth date, birthplace. And then if we keep going, right, movie.country can be connected with a country type, which has more information about this place. We will expose such ontology self-authoring tool to all Alexa developers so that you will be able to extend the ontology definition based on your need. After we have the ontology defined, let's see how we are going to actually build the graph by linking different entities or actions together from different sources. As the same entity usually are provided by different sources and providers, we have to find a way to aggregate them and linking them together. Actually, in normal cases, different providers are describing the entity in different ways. For example, Prime Video has the Avengers Endgame. As you can see, the title actually is called Marvel Studios Avengers Endgame. How about IMDb, right? The title is called Avengers Endgame with some release year in the end. Even those two are different slightly. If we keep going, right, for Wikipedia, Fandango, they may have different descriptions about the movie. Even sometimes they have different genre, right? Many different metadata properties about the movie. From a human point of view, we may be able to understand, okay, they are actually talking about the same thing, same digital movie entity. But for Alexa, right, in order to understand this, connecting the dots, we need to introduce this entity linking technology. Currently, we are building a machine learning-based solution to aggregate the data from different sources, such as applying, blocking, matching, different machine learning techniques, so that we know, okay, they actually can be joined with a single representation into the graph. The entity linking solution also helps us to detect the duplicated entities, types in the graph. It also provide us an aggregated way, very comprehensive representation of the linking data. This signal is really important for us to perform entity resolution tasks, as well as to improve our search ranking accuracy. With this linked entity and actions, we will have the knowledge graph to be constructed offline. But how this offline construction, entity linking, right, this piece can be connected to the Alexa overall end-to-end runtime architecture. So let's do a quick recap. This is the Alexa end-to-end runtime architecture. And today we highlighted, right, zooming into the natural language understanding and the entity resolution piece here. Now, if we keep zooming in and look at the Alexa voice service first, we will take the recognition results from Alexa voice service, sending to natural language understanding and entity resolution service to perform language understanding, generating intent slot information we need, constructing the graph search query now, sending it to the knowledge graph. Now, this knowledge graph will be able to retrieve the list of entity action pairs based on the search query, as well as returning the action to provider links along with those. The entity action pairs will be ranked jointly with the data retrieved candidates from all other sources by cross-source re-ranking. And we are trying to make sure we are returning the most relevant entity action pair to you as the top result. Once we returning the entity type, action type retrieved, we will further influence the interpretation accuracy from NLU. And then this intent will be route to the proper right skill providers. They know what action they should take. In the end, they can complete this task based on the overall architecture's results, right? Based on the entity action we recommended. With the power of this knowledge graph now, you can see the system will be able to transform some utterances like Alexa, play the opening song from Robert Downey Jr.'s latest movie, to something like more direct, Alexa, play Dear Mr. Fantasy by Traffic. And then we will be able to route that traffic, that request to the right provider, because we know the provider links all the proper provider capabilities to complete this task. As Jeff started with the skill example, he showed you how you could leverage ER techniques to provide a better customer experience. I would like to remind you where you can find all those useful content so that you can build your skill, help your skill development using ER solutions. This is the link where you can find all the skill development content. You will find it useful. And hopefully, some of the technologies we are working on right now will be there in future. Just stay tuned. Entity-based task completion is a pretty tough, hard problem, as you can see from this talk today. And we made it even harder because of the voice interface, because of the diversity of all the use case we are supporting. But beyond the task completion, it will be even more harder, like supporting conversational AI and powered by the entity action knowledge graph, thinking about how we expand, right, the knowledge graph to support natural conversations. And to further enable more capabilities through such entity action knowledge graph to all the developers, to delighting our customers further, yeah, that's our future challenges we are facing. So as like Star Trek, our journey continues. Even though we solved many, many of the problems, but hopefully I made it clear. There are still a long way to go. And at what we like to say at Amazon, it's still day one. And today here, I hope you will continue this journey with us as a customer, as a skill developer, as an engineer or researcher to help us to create this future by building it. All right, thank you.